Welcome to the 2016 NASA Ames Summer Series. Biology is a magnification of the physical laws and structures that it is made of. Planets, until recently, have been thought to be unique, but the Kepler mission has demonstrated that they are a ubiquitous part of the physical universe and just a reflection of the physical universe. K2 has taken the Kepler satellite that's lost its ability to maintain its long-duration pointing stability and created a new mission that observes the fields along the ecliptical plane. What discoveries await? Today's presentation, entitled Microlensing and the K2 Experiment, will be given by Dr. Thomas Barclay. Dr. Barclay is the director of the Kepler K2 Guest Observer Office, where he is, in part, as part of the duties, responsible for performing Kepler and K2-driven investigations. He received a Bachelor's of Science in Physics from the University of Leeds, followed by a Master's of Science in Astronomy and Radio Astronomy from the University of Manchester. He then went on to receive a PhD in astrophysics from the University College London. Several notable discoveries that Dr. Barclay led include the detection of the smallest known exoplanet and characterization of the first super-Earth-sized planet orbiting close to its star's habitable zone. Please join me in welcoming Dr. Barclay.
Good morning, everyone, and thanks for coming. And hopefully you're all well and rested from the three-day weekend, so you'll be awake for the entire presentation, which is going to be a really great thing. I'm going to talk about K2, the K2 mission, but I'm going to start actually by talking about the Kepler mission. We use the Kepler spacecraft for K2, and the Kepler mission I think was one of the most important missions we as an agency have ever done. It can truly say that it's redefined where we see ourselves in the universe. What is our place? Where do we come from? Where are we going? It's telling us about ourselves, and I think that's really, really wonderful and fantastic and changes our paradigm. So the Kepler mission's goal was to determine the fraction of habitable zone planets that are Earth-sized in our galaxy. And I think the mission has really done this, and it's told us that there are planets everywhere, and that once again, we learn that we're not especially unique or special out there, at least in terms of where we live. So just a brief mention of how we find planets. What we do is we look at stars. Planets pass across the face of a star. Is it still going? Yes. Let's show it like this. This is even better. Planets pass across the face of a star, and when they pass across, they block a little bit of the star's light, and that dimming we detect. We call it a transit. We named this transit after things that happen in our own solar system. This is our own solar system. This is the sun, and this is Venus passing in front of it. Fortunately, I got to see 2 transits of Venus. If you didn't see one, you're going to hope that you live well, eat well, and live for another 100 or 200 years because they don't occur very often. Certainly not again in my lifetime. But this is the transit of Venus. You can see some really wonderful things like this. Do you see this jittering on the surface of the star, of the sun here? This isn't just the projector putting noise in there. This is actually what's going on the surface of our star. This is granulation. This is motion, convective motion coming up. And one of the amazing things about our spacecraft and what it does and how sensitive it is that this granulation noise and surface noise and convective features is actually what limits our ability to find planets among many of our stars. It's the stars themselves are too noisy, and they limit our detecting ability. I think that's really wonderful. But you see some nice things there about finding planets. You see the limb of the stars darker than the center of the star. This is what we call limb darkening. We see this in our Kepler data. You even see a little bit of the atmosphere of Venus, and I think the next 20 or 30 years of our agency's exoplanet hunting and search will be to try and model the atmospheres of other planets, not just ones in our own solar system. So why is it so difficult? Why didn't we find lots and lots of planets until we had a mission in space to detect them? Well, this is what Jupiter would look like transiting the sun. You see it's pretty big. It's about a tenth the radius of the star, therefore blocks out about 1% of the area. It's fairly easy to detect. We call it a 1% transit, a 1% dip. We see these from the ground. These are amongst the first planets kind of found. Now let's look what Earth would look like. Do you see this tiny dot up here? Here it is. That's what Earth would look like. The amount of light blocked by Earth is about 100 parts per million. Now, to put that another way, just imagine, there's 1 million photons coming from this star, just 100 are blocked by this planet, and yet we can detect these things. In fact, we can detect many of these things. But we needed to build a special instrument. And so I just have a little short movie here showing some of the heroes of this story. We scientists get to talk a lot about the results, but it's the engineers and their ingenuity that time and again has enabled us to both build a wonderful instrument and then keep the mission going and keep it operating. Throughout this talk, I think everything we've done is dependent on the ingenuity and the resourcefulness and the childlike excitement of brilliant engineers. So I'm just going to go back to the start, and I'll just show you some of the components of the spacecraft. This is our mirror. It's a 1.4-meter mirror. It goes at the bottom of the spacecraft. This is our camera up there. So you'll see some images that look like this camera. They have the same shape. This is actually a movie, but they're moving very slowly. But that's the solar panel. And later on, the solar panel is going to become very important for what I'm going to tell you. This is just the thing arriving at the Kennedy Space Center for launch whilst they unpack it. And here they are, just putting everything together. And again, you see this spacecraft. You see the solar panel here, which became very important. So the mission launched in 2009, in March, and since then has been operating, firstly as a Kepler mission and now as the K2 mission. As aboard a Delta II, for those of you interested. One important thing to know about the spacecraft, and for the microlensing component, this is absolutely essential, is that Kepler doesn't orbit the Earth. Kepler orbits the Sun and trails the Earth in what we call an Earth trailing orbit. Actually, as time goes on, Kepler gets further and further away from Earth, and communication bandwidth decreases as a function of time. And eventually it will drift and drift and drift until it goes behind the Sun. This is with the main Kepler mission, which lasted until 2013. We looked at a single patch of sky the entire time, a region of the sky in the constellations of Lyra and the other Cygnus. That's the constellation that was escaping me. And you see here, this is the picture of the camera, that camera that I was showing you earlier on board. It's about 100 megapixels or so. It has 84 CCDs. Arranged in this pattern. And so when you see big images of ours, the reason they look like they do is because that's what our camera looks like. And the bottom left here is actually an image of some of our data. People don't often show real Kepler data. They show lots of the results, they show lots of artistic images, but they don't often show the data. And there's a very good reason for that. Our data doesn't look like Hubble data. Hubble data, essentially you need to take it, you put it up as an image, and it looks beautiful. And then people work to make it look even more beautiful, but the beauty is intrinsic to the image. The beauty isn't intrinsic to our images. Our images look like fuzzy blobs. They're somewhat large blobs. These are the stars, and this is where the magic happens. But simply all we do is we take essentially a photograph every 30 minutes, continuously. We did that for 4 years, of the same different regions of these, where the stars are, these fuzzy blobs. So you have a nice time series of images, just like this one. But what can they tell us? This is actually how we find planets. And there's so much information in this time series. I showed a little bit of the movie of what a transit would look like But remember, stars here are just blobs. We see them actually, they're what we call point sources, in that we don't resolve the stars. We can't tell the brightness across the surface of a star just from the image. They're just a single point of light that then gets dispersed a bit. So you can't physically see a planet passing through the middle of this. You just see the integrated light of the point source decreasing. And that's what you're seeing here. This is actually some real data. It's actually some early data, but I think it shows nicely of what a planet looks like. You see this random scatter, this kind of small level scatter across the data. That's the noise from the surface of a star, in addition to some of the noise from our instrument. You see regular dips on top of this noise, or dips down. The size of these dips tells us that there's a planet there. There's a planet crossing across the surface of a star. And the depth of the dips tells us about the ratio of the size of the star to the size of the planet. It's actually the ratio of the area. It tells us what percentage of the area of the star are we blocking. So if we block, if we know how big the star is, and we know what percentage of light the star is being blocked, we know how big the planet is. It's just simple as that. The other thing we can tell is by how frequent the dips are, we can tell how fast the planet goes around the star, its orbital period. Earth would have one transit every 365 days. That's all it is. By knowing how fast the planet goes around the star and knowing how big the star is, we know how far the planet is away from the star. We can start to understand how much energy the planet's receiving from its star, and then our imaginations go wild thinking about what kind of biology could be on the star. And there are actually lots of experts who know a lot more than we do, and really turning this from being what in my mind is amazing science fiction into science fact and wonderful, in-depth, real new understanding about where we come from. So this is what I was saying, turning pixels into planets. We start off with this fuzzy blob. This is one star here. We measure it continuously for several years, and we get up the thing in the center. This is showing that dip here. This is the transit. This transit's just less than, it's like 1 part in, 1 part in 10 to the 4 or so, or 10 to the 4. That shows us that was the first rocky planet we ever found. This planet was about 50% larger than the Earth. It's the first terrestrial planet we knew of outside of our own solar system. And then there's the artistic image in the bottom right, because we like artistic images. So this really tells a story of what the Kepler mission did, and why I think when I use a lot of superlatives to describe the impact of this mission, I don't think I'm overstating things. This is our understanding in 2009 of what the planets outside our own solar system did. So the first planet was found in 1995. That was 51 Peg, first planet outside our own solar system. And then since then, there was a number of discoveries, most of them very large planets, most of them things Jupiter size. So this is a graph here. The y-axis, the vertical axis, shows the size of a planet, and the relative to Earth, where Earth's at 1, Jupiter's at 11, Neptune's about 4, and the orbital period of the planet, so it's the planet's year. You can see there was lots of giant planets. There were some hot giant planets in pink. These are ones found by the transit method, the method that we use with Kepler. And then there are a few smaller ones found, but nothing really that was definitely Earth, looking like Earth. There was really a dearth of planets around Neptune-sized. So before we launched Kepler, we didn't know if Earths were rare or common. We didn't know if Neptunes were rare or common. Are most planets Jupiter-sized? You know, the most things we found were Jupiter-sized, but that's because that's all we could find. And this is what happened over the next 4 years. Bam. There's about 4,600 planet candidates in here, of which so far we know 2,300 of those are real confirmed exoplanets. So this has gone from knowing of tens of planets Jupiter-sized to knowing that there are thousands of planets out there. And most of them, interestingly, aren't like the Earth. They're not like Neptune either. They're in this middle range between Earth and Neptune, what we call super-Earths. Super-Earths are wonderful and fantastic because we don't have any of them in our own solar system, so we really don't understand very much about them. You know, if we find something Earth-sized, we can make a good guess that it's maybe like Venus or maybe like Earth. If we find something Jupiter-sized, well, maybe it's like Jupiter. If we find something super-Earth-sized, we really don't know. So it's an exciting time trying to learn what these are made of and why they're so common. But you can see there's no planets out here. So this is 2013. And since then, when the mission stopped, and since then we've been working extremely hard to develop our algorithms and software to improve our detection methods and methodologies and signal to noise. So we can find these, we can dig in the noise and find the planets out here, which is where we were really hoping to find exoplanets, because at least as far as we can understand, planets like ours have liquid water, and they are the size of ours. So we were trying to find things in that regime that are temperate enough to have liquid water, perhaps. And so this is the latest as of the latest planet candidate come out in 2015. There are very little updates since then, but there'll be another update later this year. And you can see that finally we're starting to find small numbers of planets out at this Earth region. That means we're sensitive to Earth-sized things, and we're finding Earth-sized things at orbital periods of 1 year. This is places like where we live, perhaps. And the next mission is going to try and understand them. Do they have atmospheres? What are they like? Do they have water? This is the future. This is, for the interns in the room, your generation is to help us learn and help us understand, or even just to exist at the time when we're finding atmospheres on other planets. Okay, so as I mentioned, one of before Kepler launch, we knew of just Jupiter-sized things. So are they common? The answer is no. Jupiters are extremely rare. If you look at what we find very few Jupiter-sized planets. Other detection methods are finding the same thing. Jupiter isn't a common thing. In fact, if you found another Earth-sized planet in the habitable zone, it probably doesn't have a Jupiter companion. The most common things we're finding are sort of Neptune, super-Earths and Neptunes, and then a good number of Earth-sized things. When you correct for our detection sensitivity, you find that probably the most common planets out there are things that are Earth-sized. I just wanted to touch upon some of the individual discoveries, a lot of them led by people who work within NASA Ames, along with some wonderful external scientists who've been involved with our team. This includes things that are the first Earth-sized planet, the first Kepler 22b, the first planet inside of its habitable zone. And then as we move along, the first Earth-sized planet inside its habitable zone, this is Kepler 186f, and the first sort of super Earth-sized thing orbiting within the habitable zone. None of these are quite Earth-like yet, so these are just the most exciting planets we've discovered so far, but I think we're moving towards, every step we make, things that remind us of Earth. And if you think we've found these thousands of planets, we must be looking at a lot of the sky. Actually, no, we look at one tiny area. This region just shows you the tiny span where we're finding planets with Kepler. In fact, it's even smaller than this, because we can only find planets that cross in front of their star. But of course, the vast majority of planets don't cross in front of their star. Their ecliptic plane isn't angled towards us. Therefore, we don't find them. We only detect a few percent or less than a percent of planets around their stars. So while we've found thousands, the galaxy's huge and we detect very few. So there really are truly planets everywhere. So unfortunately, the Kepler mission came to an end after 4 years in 2013. In 2012, we had a good inkling that our time operating the Kepler mission was going to come to an end. We lost a reaction wheel. So on the spacecraft we launched, we have 4 reaction wheels. You can actually see them here. These are wheels. These things, and they're not actually pointing to the wheel. Those are wheels. These actually, this is how we point the spacecraft. You have wheels, you have them orthogonal to each other, and you spin them. And by spinning in the right way, you can turn the spacecraft, or you can hold it pointing steady. The solar wind is constantly blowing towards us, and it's trying to turn the spacecraft. And so we need to counteract that by spinning wheels. It's very simple. It's nicely just using angular momentum to keep us pointing. Unfortunately, losing one is OK, because you still have 3 axes in 3 dimensions, and you still have 3 wheels. Losing 2 is not good. And in 2013, we lost the second of these. So that meant that we have 2 axes and 3 spatial dimensions. And many people thought that that was the mission over. In fact, here are some nice headlines I found. Kepler planet hunting suffers major failure, says NASA. That was it. Perhaps that was it. Perhaps that was the end of the mission. Rest in peace, Kepler. NASA gives up hope of fixing it. One thing you should learn about engineers is I think they never give up. Even if they're told they have to give up, they're going to keep digging away. And I think talking to some of the engineers at Ball Aerospace and here at Ames who are involved in this, the time when Kepler broke and things looked pretty dire, I think they had the most fun they've ever had in their entire lives. NASA missions are fairly restricted. You know, you don't want to draw outside the lines because your spacecraft's operating, it's operating well, and you don't want to break anything. And it's very easy to break things in space. But suddenly you had something that was broken, and you couldn't make it more broken. It didn't work. So you're allowed to do anything within reason, anything you like to try and fix it. All wacky ideas were entertained about what we could do with a spacecraft. And you got to play doing all these things that at graduate school and undergraduate you learned about operating. So this is the next report that came out. All is not lost. Suddenly someone had an idea of how we can keep going, and Hubble spacecraft now on the hunt for a new mission. So this was great. What was this new mission? This new mission was the K2 mission. Many people say, why is it called K2? Why is it not Kepler 2? Well, my answer to that was, well, it's named after the mountain, K2, not Kepler. While Everest may be the highest mountain, a higher proportion of people die climbing K2. So I thought this was an appropriate metaphor for our mission, an extremely challenging thing that, to do and to try and keep operating. So how does this new Kepler mission work? So you have 3 axes. I brought a model. I have a prop. So you have 3 axes. And if you think you point it like this and your solar pressure goes like this, you're going to roll like this and tumble. And you might be able to hold 2 dimensions, but you're still going to start to roll and you're going to start to tumble. So what the engineers realize is we need to find a way to balance the spacecraft, to hold the spacecraft in fine pointing with the 2 reaction wheels and then balance it against the solar pressure. And then once you come up with that idea, the answer is fairly simple. The solar pressure comes at you like this, so you need to point like this at the sun. You can hold the pitch and yaw steady. You guys are the sun in this image. Pitch and yaw steady, that's this way. And then all that's uncontrolled is this roll vector. So if you point your solar panels, the thing I told you would be important, at the sun so that they're finely balanced, so the spacecraft looks symmetrical in the normal to the sun, you minimize roll, and you can balance your spacecraft, you can point precisely right over here, and you can operate your mission again. So this ridge, this is what we call the balance point. And this is just another image showing you this way, down the bore sight of the spacecraft. And you can see what we need to do is we need to find a way so that the sun coming from here is just balanced. And so we spent several months commissioning the spacecraft, essentially learning what the spacecraft looked like in the normal to the sun. So our commissioning involved us pointing at a field of the sky and seeing how much we re-roll, and then changing that angle of it and seeing how much we roll, until we learned where the balance of the spacecraft was. And amazingly, we were able to do this. We were able to learn the shape of the spacecraft in space and point the spacecraft precisely using wheels and by balancing it. Now, it's not a finely precise balance. It's an unstable equilibrium. Eventually, you're going to roll one way or the other. So the way we control for that is that if we point it, we start to roll. If you roll too far, we fire a thruster, which puts us back. And the thrusters are on here. It puts us back to where we were. And so you have this continual motion of pointing, roll, reset, roll, reset. And we do that about every 6 to 12 hours. So this was the nice headline. I thought this was well described exactly what we're doing there. That description, Kepler resurrects planet hunting. NASA resurrects planet hunting Kepler with broken parts with magical sun. So I thought that was very nice. So yeah, magical sun. But because of what we're doing, this actually limits us, but also created our mission and created what we're doing. Our limitations, though, that we could only look for at a part of the sky for about 80 days. The reason being, if you think of again, you're the sun, and you're going around the sun like this, looking backwards. You can look at somewhere over here, and your limit is you can't go too far around or you're going to start getting light down the barrel of the spacecraft, which is terrible. You don't want sunlight down there. And then, that's around here. You don't want, and then the other side, you can't get too far around this way as you orbit the sun because you want to get the solar panel, keep having light. So that limits us to observations of, in one way, about 30 degrees, and the other way, about 50 degrees, so about 80 degrees. Because our orbital period is roughly 360 degrees, that's about 1 degree a day. So that gives us an 80-day campaign. So this is what this is showing. This is us going around the sun this way. We point at a field over here. We move around. We keep pointing. And then we point to 190 degrees away. And this is an 80 days of motion. We point backwards, so we don't get bugs on the mirror when we move. It's actually so we don't get Earth in the field of view. If you point forwards, you would get Earth in the field of view very naturally. Earth would have to pass through the field of view. Earth's extremely bright. And when we were commissioning this, we weren't sure what would happen if something that bright fell onto our focal plane. And so we decided, well, given the balance between pointing forwards and backwards is fairly even, let's point backwards. We've since learned that it's actually fine if Earth gets into our field of view. It doesn't cause any long-term damage or anything. But that was just the way we built the mission. So what happens then is you get a lot of fields observed along this ecliptic plane, the plane that our spacecraft looks out on, the plane that the Earth and Sun are in. And so this is nice. You all know the constellations in the ecliptic plane, or probably most of you, because they're the zodiacal constellations. So the first 2 years of our mission is shown in brown, probably brown here, and the next 2 years are shown in green. So these next 2 years have just been funded, so we know we're going to be at least a 4-year mission. I'm going to talk a little bit soon about the yellow arrow here. This is campaign 9. This is our microlensing campaign. We did a dedicated campaign to microlensing, and you're going to hear some of that later. I might give you a talk, or someone else will give you a talk in 2 years telling you about the next arrow, the supernova focus campaign, a single experiment dedicating to understanding supernova and the early rise of when a supernova happens. But that's going to happen sometime next year. K2 isn't just Kepler, but worse. That's an important thing. It's a very different mission. And we knew we couldn't survive being Kepler, but worse. Kepler changed everything, but Kepler took all this data and we're using it to understand around us. But I think Kepler's done. We got the data we needed to learn a lot about our universe. We don't want to collect that data again and learn the same things. We want to do something new. So K2 enables us to do that. We can do things we couldn't do with Kepler because of the way the spacecraft operates. Here are just some examples of things that we didn't do with Kepler. This is M35. This is a cluster of stars. Clusters of stars are fantastic laboratories to study astrophysics. All the stars formed at the same time, or roughly the same time. Therefore, they probably all have the same composition. So you have stars of the same composition, same age. Why do they differ? And their differences should tell you something about how old they are, how massive they are, what their radius is, what their evolution history is. Are binaries more common? Are binaries less common? What are planets like in clusters? So you can learn about how things form as the universe goes on by looking at different clusters at different ages. Kepler didn't look at many clusters. We can look at lots because we look along the ecliptic. The ecliptic's full of clusters. Kepler looked at one field. We're going to look at 18 fields. So we get 18 times the amount of area that Kepler saw. This is star-forming regions. Kepler intentionally didn't look at star-forming regions. Why is that? Because star-forming regions are full of dust, and dust absorbs optical light. And if you absorb optical light, you don't see as many stars, you don't find as many planets, and you can't find Earth-like things. With K2, that's not a limitation anymore. We look at a single field for 80 days. If it's got lots of dust, we'll just look at somewhere with less dust in 3 months. And now we can start to study these youngest stars. We can study how stars form. We can study how planets form. We can study when planets form. Do planets form right away at the same time the star? Do they take a few million years after the star? Do they form close to the star? Do they form far out from the star? These are questions K2 can answer that Kepler wasn't able to answer. These are new science we're learning. And something I'll show you a little bit of, a movie of, this is a comet here. The ecliptic plane, as we learned very quickly when we started getting our commissioning data, is full of moving objects because it looks at where our own solar system is. Our solar system forms in a disk, and so K2 is looking into this disk. And so we see thousands and thousands of asteroids, and we see planets, but planets closer to home than what we're used to. It's a little bit out of focus, but this is a cover image from a proposal we put in. But this is showing you all the constellations along our ecliptic and things that either we have observed or will observe in those constellations. And you can see this huge variety from galaxies to planets to clusters to planetary nebula, all different science in all different fields. Depending where you look, you find different things, you have different science. So I think K2 has really far exceeded our expectations of the breadth of science it's doing. It's really changed from this somewhat narrow mission of Kepler into this extremely broad mission of a general astrophysics observatory. In addition to astrophysics, we also do some planetary science work. Planetary science is looking at things in our own solar system. Here is just a quick movie of an object from our own solar system. This is the planet Neptune. And you can see something going around Neptune. That's the moon Triton. This is, I think, about 60 days of data, and you can see this planet moving. You see smear because the planet, bleed of the bright because the planet's very bright. But you can see very nicely the moon, the motion, and the orbital dynamics. You know, a lot of us learned orbital dynamics in undergraduate, in high school, in PhD at different levels. I certainly had never seen orbital dynamics happen in real time or in a movie like this as the moon goes around the planet here. You can see Kepler's laws in action in a single movie. And the reason that Neptune's moving so much isn't that Neptune's moving fast, it's that the parallactic angle of Kepler to Neptune here is changing. As the spacecraft moves around the sun, the position of Neptune compared to the background stars moves. We call this a parallax, and that's what's going on here. This is just showing you some of the other solar system stuff we're doing. This is the brightness change of some trans-Neptunian objects, things in orbit, in the same orbit as Pluto. And you can see this little wiggle in brightness as they rotate. We can learn the shapes of bodies in the outer solar system. We can learn how they rotate. We can learn how bright they are. This can help us learn how the solar system formed. The reason I'm showing planetary science stuff is because I think nobody predicted that we would do a lot of planetary science work, but it's actually become a very important part of the mission as we learn about our own solar system, and that informs us about exoplanets and vice versa. I like this movie because it's the faintest thing we ever observed with K2. This is something, for those who understand magnitudes, 23rd magnitude is extremely faint. You can see something going up and down. Do you see that? That's a trans-Neptunian object. I don't know if you can see that in the movie. You have to get your eye in. There we go, up and down. The faintest thing we've ever observed. Kepler observes K2, we observe objects from the extremely bright to the extremely faint. We have this huge dynamical range in brightness. Okay, so I mentioned clusters. Clusters is extremely important. This is an image of the Pleiades. I show Hubble images because Hubble's beautiful, as I mentioned earlier. This is a Hubble image of the Pleiades. This is actually our image of the Pleiades, the Seven Sisters, as many of you will know it, and the 7 bright stars here, which are used really heavily in astrophysics to try and understand how stars operate. Let's zoom in here, and this is showing you, this is the shape of our CCDs. This is showing you where we looked for a given campaign. And then we put masks around these, and we put masks around them, and we can observe these bright stars in this field of view. And you can see them actually because they're moving here. That's the movement of the spacecraft I mentioned, this 6-hour roll. So by looking at these, we can look how their brightness changes over time. We can look at seismology inside of these stars as they oscillate, as gas moves up and down and convex inside them. And we can understand the internal structure of these stars that people have been observing for millennia, give new insights on them. This is just, I just thought I'd show you some of the full frame images, as we call them. This is our full frame. You'll see that there are two CCDs that are no longer operating, but the rest of the area really is vast and can teach us a huge amount about our galaxy. And this is where the Pleiades is. This is another cluster, the Hyades that many of you have heard of. Persepe or the Beehive cluster falls into things. So this is a hugely diverse field and hugely new things that we can look into. Of course, K2 is still an exoplanet powerhouse. Exoplanets really is what the mission primarily seems to do. While we're a general observatory, people propose to do science, and exoplanets is obviously a very big part of this. There are more than 50 confirmed planets from K2. I think there's about 1,000 planet candidates as of yesterday. There was an announcement of about 800 new planet candidates. So K2's pushing up there towards the sort of Kepler numbers of things detected. And crucially, we're finding planets around the nearest stars, around the nearest and brightest stars, things that perhaps we can hope to characterize with missions like James Webb. So this was as of a month ago, the number of planets we're finding. And you see this actually mirrors Kepler quite nicely. Very few bigger things, many more of these smaller things, peaking in the super-Earth size regime where we're most sensitive. So this is just showing you some of the reasons why we differ from Kepler. This is a popular handout image that we gave to many people as a poster for Kepler, and then we made one for K2. And with Kepler, you thought how small the sun is. And with K2, you think how big the sun is. And that's because K2 looks at lots of nearby stars, trying to find planets around the smallest stars, these M-dwarfs as we call them. The reason being small stars have a bigger transit depth. I said transits are a function of the area of the planet divided by the area of the star blocked, or the area of the star. And therefore, if you shrink the star, you find smaller planets more easily. So that's what we're doing with K2. We're finding these planets around the smallest stars. So Kepler's taught us a lot about the inner part of the solar system, or the solar systems. It's taught us about the occurrence of things interior, basically, of Earth's orbit around other stars. But if you look at this graph, this shows you where the inner system of our solar system and where Kepler's sensitive. The blue region here is showing Kepler sensitivity as a function of distance from a star. And it tails off as you get towards Earth's orbit. And then if you shrink that region down and look at how big our solar system is, you realize that Kepler, while teaching us so much about other planetary systems, it's just a tiny window into even our own solar system. In fact, if you think of what Kepler could detect in our own solar system, Kepler might find one, perhaps two planets in our own solar system, of which our own solar system has many. So we've just probed this tiny regime. Fortunately, there's something called microlensing that may come out to inform us of other regions around other stars. Teach us things about Neptune, Saturn, Uranus, and their frequency that we simply don't know right now. And K2 is going to be an important part of this. So what is gravitational microlensing? Very, very simply, gravitational microlensing uses the fact that gravity warps space-time. So if you have a lot of gravity and you have a background star, the light from that or a background galaxy as traditional microlensing, the light from that galaxy is going to be bent, it's going to be focused. And so you see that light, these background galaxies, as brighter than they would actually be. This is the traditional gravitational microlensing. It's been used for a long time to weigh foreground galaxies. You can understand the mass of things by how much they bend the light. Microlensing, that was gravitational lensing. Microlensing uses this effect, but on the much, much smaller scale. You take a background star, a star in our galactic bulge, say, in the center of our galaxy, And then you have that light coming towards you, and then you have a foreground star, perhaps even a star that's too faint to see. But the light of that background star is bent around the foreground star. So as that foreground star moves past, because everything's moving, moves past the background star, you see the background star get brighter because the light is focused towards us. We call this a microlens. And so that's what you're seeing here. Background star, foreground star moving, and you see this shape of the brightening. But what if this foreground star had a planet? You'd see two dips. You'd see first the main dip of the microlensing of the star, and then a little dip caused by the lensing of the planet's causing. And this is a microlensing event. So this goes up, and you see the secondary dip. That lasts, of order a few hours to a day, and the main event might last a few weeks. We've detected a few planets like this, but very few, and the Kepler mission is going to help us detect many more of these. This is a brief movie I'm going to show, showing you how this effect works, not just for stars with planets, but also perhaps for free-floating planets. The idea is that there's planets orbiting no star, wandering planets, or rogue planets. I call them free-floating planets. So in addition to finding planets around distant around their own star, we can also find planets that orbit with no star. So this is just the microlensing effect. This is the lens here, move across. This is the foreground star that you can't see, warping the light. And then you see this ring as it focuses the light towards you. And then when you add up all that light, you see this brightening. So K2 is going to look towards the center of the galaxy where there are the most stars. You have the most chance of something passing in front of a background star. And it's going to try and find these events by looking a large patch of the sky towards there. If we just look at what Kepler probed in this tiny region, we can see that in comparison is very small compared to where the microlensing region is going to probe. The microlensing region has a much more higher volume of space where it can find events towards the center of the galaxy, looking for these very faint stars that pass in front of these background things. So, but why K2? These microlensing events have been observed from the ground, some wonderful ground-based observing projects to detect them. And they've found planets. They have found a few low tens of planets. Kepler gives you something else. Kepler isn't orbiting Earth. It's far from the Earth, in fact. As I mentioned, it's about 8/10 of the way to the sun is the distance that Kepler's away. So that means that Kepler and Earth look at a different angle towards these microlensing events. And these microlensing events are extremely precisely tuned. And the shape of this brightening is very precise and very sensitive to the angle that you're looking at it. So if both of them look at a slightly different angle, they see different things. The events look slightly different. This is just an example of what something would look like here. You see the microlensing event from Earth, and you see a slightly different time of center and a slightly different magnification from what the spacecraft, the K2 mission, would detect with the Kepler spacecraft. And you can use these differences in the shape to learn things about the unseen lens star, primarily, and the unseen lens planet, hopefully. Primarily, you learn about its mass. You learn how massive these planets are. Without the extra line of sight, it's very hard to uniquely determine the mass. I'll skip that one. Of course, doing this requires a lot of ground-based observing. The Earth is a challenging place to look at continuously. K2 can look at a place continuously fairly easily. We just point. On the Earth, there are two reasons. One, the Earth rotates and you have daytime. Two, you have weather, you have clouds. So because we wanted to observe this region simultaneously from Earth and space for 3 months with no break, we put together a huge network of telescopes to observe. This is just some of the telescopes that are observing these regions of sky continuously, both doing observing of large regions and also follow-up of events that are found. These telescopes, I think, most of them are observing every single night for the campaign 9, which ended a few days ago. It was, and most of these are manual, so you needed people observing at the telescopes for 3 months straight for all these telescopes. I like to think that we actually observed the microlensing region for more than 24 hours a day because we had multiple telescopes going simultaneously for 3 months. And so that meant that when there's weather and when there's daytime, there wasn't a break. This is just the first image that we pulled down from the spacecraft. This is our full-frame image. This was made courtesy of Doug Caldwell, who works within the project. And I just wanted to show you what this looks like. It looks nothing like any of our previous full-frame images. And that's because it's just packed with stars. There's stars everywhere. And this is like looking at the Milky Way. In fact, if any of you have been lucky enough to be in the southern hemisphere, it's like looking in the Milky Way in the southern hemisphere where you see more stars. And so this is a region, the dark regions where there's lots of dust. And here you see huge numbers of stars. And this is where we do some of our microlensing experiments. And as of today, there are about 500 microlensing events detected from the ground and from the spacecraft, which we hope to find planets in. It's still work in progress. The campaign stopped over the weekend, and but we're going to be working hard to find more events as time goes on. I'm just going to stop here and saying that this isn't the end of the story. Microlensing we understand as an agency to be an extremely valuable way to determine what other planetary systems are like. Kepler told us about the hot planets, the planets that are hotter than Earth and equal to Earth. K2 and WFIRST in the future are telling us about the cold planets. WFIRST will launch in 2024 and will be detecting thousands of Jupiter-like planets and Neptune-like planets, and maybe cold Earth-like planets orbiting their distant stars, and hopefully lots of free-floating planets orbiting no-star, rogue planets. So all I say is just thanks for coming, and stay tuned for our early estimates of microlensing events when we find them that will be coming out over the next 12 months. Thank you.
Very good. Thank you. So we have time for some questions. If you have a question, please raise your hand and wait for the microphone. Ask one question only. Thank you.
Hi, Richard Archer, University of Colorado. Thank you for that great talk. I have a question regarding the regions of planets that are detected. You had mentioned that there's an issue of sensitivity in terms of noise versus detection, and it's in this sort of Earth analog, or Earth region. I'm wondering if you are aware of the Starshade project, and I'm wondering if you have any information regarding that, how it's proceeding, if it's proceeding.
Yeah. Our limited sensitivity at Earth sides come because when you build a spacecraft, you tend not to fund it to do things far and beyond your what you want to do. You want to come in as cheap as possible, but still do amazing science. So you make what you want to do just possible. And so that's why we're not detecting many, because it's extremely hard, and our mission ended after just 4 years. However, we are finding things, which is really fantastic. The Starshade project is just mind-blowing. It really is. You launch a spacecraft to look at a star. You then launch this huge thing that can be, tens of meters across, looks like petals of a flower, to block light from the star. And by blocking light from the star, you can start to see the planets around the star. If you look at a star in the sky, you can't see planets, even if your eyes were incredibly sensitive, because you're swamped by light from the star, swamps any light coming from the planet. But if you use very clever optics to block out light from the star, you can see the planets. These star shades are going to orbit millions of miles from the spacecraft. It's an incredible undertaking, but there are plans that the star shade is going to be launched perhaps in the 2020s. There are certainly investigations going on right now, perhaps even as part of the WFIRST experiment. It's a very much an exciting new area of research, but it's very challenging to do. One of the reasons is you can look at one star over here, and then you have to move your star shade millions of miles in order to look at another star in another part of the sky. That and the optics are incredibly hard to create. But I think coronagraphs, which are much smaller things to block the light, and star shades, which are much bigger things, but orbit far from the spacecraft, are going to be how we're going to find and understand life outside our own solar system. Because you can actually image the planets themselves. You can see directly the light coming from these planets. You can understand perhaps what's in the atmospheres of these planets.
Hi, I'm Morgan from Florida Tech, and I was wondering what the most common solar system configuration is for exoplanets, and if we have enough data to speculate about that.
Kepler really, it probes the inner solar systems. It doesn't probe the outer solar systems, but other things do. I think the average solar system doesn't have many giant planets. The average solar system probably has planets closer in than ours. We're probably a little unusual in that we don't have anything interior to Mercury. That said, the universe is so large that I think if you, but the number of parameters so high that if you looked at any planetary system, you'd say this one's unique for reason X. But because there's so many parameters, every planetary system is unique. And we can point to things in our solar system that are unusual, but unusual things happen all the time. I think one thing we have, as we increase our knowledge as a species, we learn how insignificant we are. And we're just learning that again. Planetary systems like ours are likely common. Maybe not the most common, but they're certainly not rare.
Hi, I'm Garima, and thank you for your talk. You mentioned earlier that there's a focus on refining algorithms to find planets that are the same size as Earth, and I was wondering why the priority is on finding the same size instead of maybe the same energy, or why does size make a planet more inhabitable? Why can't we inhabit bigger or smaller planets?
Yeah, the Kepler mission was focused on finding planets like ours, so orbiting stars like ours, orbiting planets at distances like ours, and sizes like ours. The reason being is we have a sample of one planet with life, and we extrapolate from there. I think probably anybody, if you explained that you discovered one thing and you're going to extrapolate to the universe, any kind of statistical person will critique that method somewhat harshly. But that's all we have, and that's what we do. We know life on our planet needs liquid water, and we need our solid surface. We don't have life that just, or at least not much life that floats around with no surface. Perhaps it exists, but it's probably hard to detect. It wouldn't be complex life like we have, probably. So the reason being is because we know that we exist, therefore we look for places that look like our own. It's probably not a very good strategy, but it's the least worst right now.
So please join me in thanking Dr. Tom Barclay for a great, excellent talk.